Hi everyone, my name is Mark Vinciguerra. I'm a specialist solutions architect at AWS on the ML Frameworks team, and today I'll showcase how to efficiently orchestrate multi-user AI/ML training and inference jobs on SageMaker HyperPod cluster orchestrated by EKS. This will be a three-part video series, where each part will cover the following ideas: overview of ML key concepts on AWS, distributed training on HyperPod, and inference on HyperPod. For this video, we will explore essential machine learning infrastructure components within AWS. We will examine AWS HyperPod architecture, its implementation in the AWS environment, the critical role of system resiliency, Amazon Machine Images, or AMIs, container technology, and comprehensive deployment strategies. Through this discussion, we will establish a foundational understanding of these key concepts before we start our demo. Now, let's go into why we are talking about HyperPod. Over the last few years, the computational demand to train and deploy GenAI models have been exploding. With new architectures and techniques, we went from models with millions of parameters to models with billions plus parameters. At the same time, the underlying architecture and techniques have advanced. For example, from convolution-based networks to transformer architecture to mixture of expert models and reinforcement learning fine-tuning methods. As model sizes grow and techniques evolve, the demand for training and inference infrastructure grow as well, and there's a need for smarter orchestration, resource governance, and operational flexibility. As models grow increasingly complex, we need to understand and address 5 key challenges that significantly impact our training and inference process. First one is hardware failures. In large-scale clusters, hardware failures can interrupt both training and inference workloads. In synchronous distributed training, a single node failure may stop the entire job. In inference deployments, a hardware issue can reduce throughput or disrupt user-facing services. As clusters grow, the probability of failure rises, increasing downtime, manual intervention, and costs. We need infrastructure that tolerates failures, network issues, and system crashes with minimal impact. The next point is underutilization. Rigid resource allocation in ML clusters forces a trade-off: over-provision and pay for idle capacity, or under-provision and risk performance shortfalls. As a result, expensive accelerators sit idle during low-demand intervals. We need smarter resource orchestration and elastic allocation across training and inference workloads. To the next point, scalability. When it comes to scalability, there are operational challenges from network bottlenecks to orchestrating thousands of specialized accelerators. As workload demands surge, organizations must build infrastructure that can scale efficiently while managing costs, requiring sophisticated systems for everything from automated recovery to optimized resource utilization. Cluster customization adds complexity and slows development. What do I mean by this? For example, building and maintaining custom AMIs, drivers, network configurations, and devices like attaching EFA on an EC2 instance pulls engineering effort away from ML development. With that said, users should still have the option to be able to customize their ML stack to their liking. Finally, observability. Without comprehensive visibility into infrastructure health, model performance, and system metrics, teams can struggle to diagnose bottlenecks or optimize utilization. Insight into task and cluster level behavior is very essential. Generally, training and hosting models involve more than just the price per GPU hour. It's about maximizing productive time. Stable, reliable clusters allow teams to focus on training, evaluating, and then deploying world-class models instead of troubleshooting hardware issues or software dependencies. By investing in a reliable infrastructure and the right tools, your cluster will work harder for you, and you spend far less time debugging and maintaining it. These are the reasons that in this video series I'll be demoing Amazon SageMaker HyperPod. HyperPod provides a comprehensive solution for scaling generative AI development across tens to hundreds to thousands of accelerators, delivering a purpose-built infrastructure that removes the complexity of building and managing large-scale ML environments. With built-in fault detection and automated recovery, HyperPod makes sure that there is continuous operation of critical workloads, automatically repairing infrastructure issues, and resuming operations from checkpoints without human intervention, essentially operating as a self-healing cluster. The service combines automated resource management with centralized governance features, which enable teams to efficiently distribute training and inference workloads while maintaining centralized control over compute allocation and task prioritization. It also offers optimized recipes to get state-of-the-art performance while quickly getting started training and fine-tuning publicly available generative AI models. This includes Llama, Mistral, and DeepSeek models. Alongside this, you get integrated tools for experimentation and observability. Via a one-click deployment of Amazon Managed Grafana and Amazon Managed Prometheus, you can monitor infrastructure and get task-level metrics, and via SageMaker ML flow, within SageMaker, you get experiment tracking, model versioning, and traceability of parameters. HyperPod also provides Kubernetes native operators, the HyperPod training operator for distributed model training, and the HyperPod inference operator for model deployment. We'll dive into these operators in the next few parts of the series. Now let's look into what HyperPod consists of. Starting from the top, HyperPod offers flexibility in its job orchestration layer where you can use either Slurm or Amazon EKS, completely up to you. For this video series, we'll be focused on a HyperPod cluster orchestrated by EKS. On the frameworks and libraries layer, you have full control over which tools you'd like to use for your training and inference jobs. For example, for job submission, you can leverage open source tools like Ray, RunAI, PyTorch, Flight, SkyPilot, and more. For observability, you can use tools like Prometheus, Grafana, MLflow, Weights and Biases, and CloudWatch. For development tools, you can use tools like Studio, Kubeflow, or notebooks. Below this, you have the flexibility to bring virtually any framework, including PyTorch, TensorFlow, Nemo, and JAX. For communication, you could choose between NVIDIA Collective Communications, or NCCL, or AWS Neuron Runtime for AWS Trainium or Inferentia instances. The infrastructure layer provides the essential trio: compute, access to powerful accelerator instances like GPU instances and Trainium; storage, multiple options for storage including S3, EFS, and FSX for Lustre. Finally, networking, optimized with EFA for high bandwidth and low latency networking. Now let's zoom into the lower half of the stack. Let me walk you through the ML software stack architecture on AWS, starting from the foundation up. We have our EC2 instance. As an example, we can have a P6 B200.48x large instance with 8 B200 GPUs and 3200 gigabits per second of EFA networking across 8 400 gigabytes per second EFA network interfaces. This will be running our operating system. We're on HyperPod, Slurm deployments use Ubuntu, and EKS deployments use Linux. Then we have our kernel space, which contains several critical components: GPU drivers for accelerator management, EFA Elastic Fabric adapter for high-performance networking, GDR copy for direct GPU memory access, and Lustre client for high-performance file system access. Within the operating system, we integrate key communication and computation libraries: NCCL for GPU to GPU communication, CUDA for GPU computing capabilities, libfabric via EFA for optimized networking performance, and a distinctive feature is the SageMaker HyperPod extension within its AMI. And this includes health check agents for system monitoring, auto-resume capability for fault tolerance, support packages for both Slurm and Kubernetes orchestration. And an important integration point is the AWS EFA installer, which is the EFA software installation files, which enables seamless use of libfabric as a network provider for NVIDIA NCCL-based applications. Moving to the right is where we have our virtual environments and containers, where we run the training and inference code inside an environment that includes CUDA, NCCL, and libfabric-enabled networking libraries. This allows direct GPU access from within containers and supports distributed multi-node, multi-GPU workloads. We will also have our training code as well as the required libraries for our code to run. Now that we've taken a deep dive into what an instance looks like, let's zoom back out to see the full picture. So this is an architecture diagram of a HyperPod cluster orchestrated by EKS. This architecture involves 3 distinct VPC environments working together. Starting with your SageMaker user VPC, this is where your primary interactions with the system take place. This VPC houses essential services, including Amazon ECR for container management, CloudWatch and AMP and AMG, Prometheus Grafana for monitoring, and SageMaker Studio for development. This is where engineers and researchers interface with the environment through familiar tools like JupyterLab, Code Editor, and MLflow. Next, we have our EKS VPC, which contains the EKS control plane in an AWS managed environment. The EKS control plane is a fully managed set of Kubernetes master components, including the API server, scheduler, controller manager, and the etcd key value store. That provides a secure, dedicated API endpoint for your cluster's worker nodes and clients to interact with. The control plane communicates with your VPC through elastic network interfaces. The third component is the SageMaker VPC, which orchestrates the compute node cluster in an AWS managed environment. This VPC leverages the Elastic Fabric adapter for high-performance computing and maintains system reliability through continuous health checks and automatic instance replacements. The pods running on your compute will connect to Amazon FSx for Lustre to provide the high-performance storage necessary for machine learning workloads. All of these VPCs are in communication with each other through cross-account Elastic Network interfaces. At this point, we are done with the overview of HyperPod and AI infra on AWS. In a minute, I will get started on the demo, but I first want to give you context of how my cluster for the demo is currently set up. At the Kubernetes layer, we allocate compute into 3 node groups. First, the CPU group, which contains 2 ml.m5.12x large instances, which hosts the system pods and infrastructure controllers. Next, the persistent GPU group. This has 10 ml.g5.8x large instances, and these handle the compute-heavy workloads. And finally, we have an autoscaling group, starting at 0 instances, which scales out based on demand during the demo. On top of that, we organize work by namespaces. We have the system namespaces, like the Cube system and HyperPod-specific namespaces, which host controllers and services. Then we have team-specific namespaces, like the HyperPod NS training team, allocated 6 GPUs for training, and the HyperPod NS inference team, which is allocated 4 GPUs for inference. These are created by task governance, which I'll explain in just a second. For storage, we use Amazon FSx for Lustre for reading our data, as well as reading and writing checkpoints. We mount it via a persistent volume claim, or PVC, in each namespace, which maps to a persistent volume, or PV, tied to the FSx file system. Now, what are these task governance namespaces? Task governance is a robust management system designed to streamline resource allocation and ensure efficient utilization of compute resources across teams and projects for your Amazon EKS clusters. This provides administrators with the capability to set priority levels for various tasks, compute allocation for each team, how each team lends and borrows idle compute, and if a team preempts their own tasks. At this point, I think we covered our bases. Let's get into the console and see how we can set up our cluster. So at this point, we're in our AWS console. If we want to go to HyperPod, what we do is we look for Amazon SageMaker AI. You can find the button here or search through it in the search bar. And once we're in Amazon SageMaker AI, we can scroll down and see that we have a tab here for HyperPod clusters. We can click on Cluster Management. Here you can see I have a few clusters. Say you want to create one yourself. You can go and press this button on the top right corner, Create HyperPod Cluster. And you could create the cluster based on Amazon EKS or Slurm. For our demo purposes, we're doing EKS. And we have 2 different setup options. We have the quick setup and the custom setup. The quick setup is all you need to do is specify your cluster name and then your instance groups, so what type of instance you'd like in your groups. And the quick configuration details will show you all the different add-ons and configurations for your cluster. And this includes networking configurations, type of provisioning mode, if you want it to be auto-scaled by Carpenter, and a few more things. If you were to choose custom setup, this is where you'd enter your cluster name, and you'd have a little bit more control and flexibility into how you want your cluster to be set up. You can either select create a new VPC, or if you have an existing VPC you'd like to use, you can select that as well. Under orchestration, you could select create a new EKS cluster, or if you have an EKS cluster already and you just want to attach your HyperPod to an existing EKS cluster, you could do that as well. And then you also have more control over which plugins or add-ons you want in your HyperPod EKS cluster. So I already created my HyperPod cluster just for this demo, and it is the hero cluster under cluster management. Once we click on our cluster, I see there's some new updates. We could just X this out. When we click on our cluster, we have our dashboard. In our dashboard, we could see the EKS cluster, and it has the status and the Kubernetes version, and HyperPod Observability, and our training operator add-on. Under Observability, you could see the different types of metrics and dashboards that Amazon Managed Grafana and Amazon Managed Prometheus are going to pull and display for you. And we'll look at these dashboards in a second. So that's under dashboard. And then we have tasks. These show active jobs that are running. We don't have any jobs right now, so there's none. Under policies is where we created our task governance policies. You can see we have 2 priority classes and 2 teams, or compute allocations. We have one for the training team, which were allocated the 6 G5 8x large instances, and the inference team, which was allocated the 4 G5 8x large instances. You could also set different priorities so teams can preempt themselves, with inference being 100 weight priority and training being 80 weight priority. Under instances, you can see our instances and instance groups. You can see on my persistent GPU group, I have 10 instances, and on my head group, I have 2 instances, which is the M5.12x large instances. And then I have a couple different groups for auto scaling. These all have 0 instances within. I have a few different because they're placed in different availability zones for inference. And you can see all the individual instances running here. Under events, you could see different events that were either created by you or the HyperPod cluster itself for more visibility into what your cluster is doing and actions performed. And under details, we have our EKS cluster information and the different EKS add-ons, as well as the networking configuration, so your VPC, your subnets, and your cluster security groups. So at this point, I wanted to quickly show you, if you were to press Open Dashboard in Grafana, I already signed in here. This is the pre-built dashboard, one-click observability that uses Amazon Managed Prometheus and Amazon Managed Grafana. It comes out of the box with a few dashboards. These dashboards consist of training, the file system, inference, cluster, and tasks. Quickly, I'll just show you what the cluster dashboard looks like. Kind of gives you an overview of your cluster infrastructure, where we have our total 12 instances, 10 GPUs, 226 gigabyte of total GPU memory, and a couple more drop-downs here, like GPU performance metrics as well. And you'll see once we start running our jobs, we'll get some more activity in this. Thanks for watching this video. Stay tuned for part 2, where we will train our Llama model with the HyperPod PyTorch training operator, showcase resiliency, and track our model and cluster metrics.